In episode 63, titled Box-Cox and Friends, Transformations for Shape and Variance Control, the goal is to use flexible transforms when log alone is not enough, because some variables remain stubbornly skewed or heteroskedastic even after you apply the usual tools. Log transforms are powerful, but they are only one shape in a broader family of possible reshaping operations, and the exam cares because it tests whether you can adapt when a default approach does not align with the data's behavior. Flexible transformation families give you a way to tune shape and variance stabilization without inventing a long set of ad hoc engineered features. In real systems, the right transform can reduce persistent residual structure, improve stability, and make simple modeling assumptions more plausible, but it must be chosen and validated carefully. The main lesson is to treat transforms as instruments. You pick them because the data's shape demands it, not because the transform is fashionable. When you can justify a flexible transform in plain language, you show both statistical maturity and operational discipline. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Box-Cox is a commonly used power transform family designed for positive values, and it provides a systematic way to reshape a variable using a single parameter. The family includes log-like behavior as a special case, but it also includes milder or stronger power scalings, depending on what the data needs. The key idea is that instead of committing immediately to one transform shape, you choose a parameter, often called lambda, that determines how aggressively you compress or expand different parts of the scale.
Because it is a family, Box-Cox can handle a range of skewness patterns, from heavy right skew to more moderate asymmetry, and it can also help stabilize variance when variability increases with magnitude.
The exam expects you to recognize that Box-Cox is not a separate modeling algorithm. It is a pre-processing choice that changes the scale to better match the assumptions of downstream methods. When you define Box-Cox correctly, you are describing a controlled, parameterized way to linearize and stabilize without guessing at dozens of separate transformations. The goal of Box-Cox and similar transforms is consistent with what you already know about linearization. Reduce skew and stabilize variance so modeling and statistical tests behave more reliably. Skewness can make averages misleading and can violate assumptions behind mean-based inference, while unstable variance can create heteroskedastic residuals that distort confidence and fit. A good transform can pull extreme values closer, spread out the crowded lower end, and make relationships look more linear on the transformed scale. This is especially valuable in regression contexts where the error structure matters for interpretation, intervals, and tests, not just for prediction. The exam often frames this in terms of residual patterns or violated assumptions, and a transform is the corrective action that repairs shape before you change the model family. When you state the goal clearly, you keep the transform anchored to a modeling need rather than treating it as a cosmetic adjustment. Lambda is the knob in Box-Cox that controls shape, allowing the transform to range from log-like compression to power scaling that can be gentler or more aggressive depending on the value. When lambda is near zero, the transform behaves like a log, emphasizing proportional differences and strongly compressing the right tail. When lambda is larger, the transform can behave more like taking a root or another power, which can reduce skew while preserving more of the original scale spacing. When lambda is near 1, the transform can resemble leaving the data closer to its original scale, which may be appropriate when only mild adjustment is needed. The important point for the exam is not the exact formula, but the intuition that lambda tunes how much you reshape the distribution and variance behavior. Because lambda is chosen to match data shape, you should view it as a fitted parameter of your preprocessing, not as a property of the underlying phenomenon. When you narrate lambda as a shape control, you make it clear that Box-Cox is a flexible family rather than a single rigid transform. Handling non-positive data is a practical issue because Box-Cox is defined for positive values, and many real variables include zeros or negatives due to measurement definitions, offsets, or signed quantities. One approach is shifting, meaning you add a constant so that all values become positive, but a shift must be justified because it changes interpretation and can distort proportional meaning when the shift is large relative to typical values. Another approach is using alternative transforms designed for non-positive or zero-inflated data, which preserves mathematical validity without forcing a potentially arbitrary shift. The exam expects you to recognize this constraint because applying a transform outside its domain is a conceptual error, not an implementation detail. It also expects you to reason that zeros and negatives are often meaningful, such as true absence, net changes, or signed differences, and your transform choice should respect that meaning. When you discuss handling non-positive values, you are showing that you understand transforms must fit both the math and the measurement process. Choosing a transformation should be driven by residual patterns and distribution cues rather than by preference, because the evidence of need is in the shape of the data and the shape of the model's errors. If residuals curve, or if spread increases with magnitude, that is a cue that the model is missing structure and that variance stabilization could help. If the variable is heavily right-skewed with a long tail, that is a cue that compression is needed to prevent extremes from dominating fit. If a log transform improves but does not fully fix these symptoms, that is a cue to try a more flexible power family that can match the specific skewness level and variance behavior. The exam often describes these cues verbally, such as large values have much higher variance, or residuals are not uniform, and expects you to pick a response that addresses the cause. Practicing this selection is about pattern recognition. You match the observed failure mode to the type of reshaping that would plausibly repair it. When you do this well, transformations become a targeted tool rather than a default habit. A subtle but important discipline is avoiding leakage by not fitting the transform on the full dataset before splitting, because fitted transforms can encode information from the evaluation period into training. Even though a transform might feel like a harmless rescaling, if you choose parameters like lambda using the whole dataset, you are allowing future information to influence the pre-processing applied to training. This risk is especially relevant when data shifts over time or when evaluation is meant to reflect future conditions, because a transform tuned on the full time span can smooth away drift signals and inflate performance. The exam expects you to treat transformation fitting as part of the model pipeline that must respect the training-evaluation boundary. A safe approach is to fit transformation parameters on the training data only, then apply the same parameters to the validation and test data, preserving a clean separation. When you narrate this, you show that leakage is not limited to target-derived features. It can also occur through fitted pre-processing. Because transforms can add flexibility, you need robust evaluation to confirm they help generalization rather than just improving in-sample fit. The right comparison is between a baseline model without the transform and a model with the transform, evaluated under the same held-out design, ideally with time-aware splits when the system changes over time. You should look not only at metric improvements, but also at stability improvements, such as more uniform residuals, reduced sensitivity to outliers, and more consistent performance across segments. A transform that improves training metrics but leaves held-out error unchanged is likely solving a local fit problem rather than capturing stable structure. The exam expects you to treat evaluation as evidence because flexible transforms can overfit subtle distribution quirks if tuned aggressively. When you validate properly, you make transforms accountable to real-world performance rather than to aesthetic distribution shapes. Communicating transformation choice is another exam-relevant skill because transforms should be presented as modeling convenience, not as data truth. A transform does not change the underlying phenomenon. It changes how you represent it so that a model or a test can handle it more effectively. Stakeholders should understand that the transformed scale is a tool for learning and that the conclusions must be translated back into original units or into interpretable percent change language. This prevents a common misunderstanding where someone treats the transformed values as more real or more meaningful than the original measurement, which can create confusion in reporting and decision-making. The exam rewards this posture because it shows you respect the boundary between mathematical representation and operational meaning. When you frame transforms as conveniences, you also reduce resistance because people can accept a technical adjustment more easily when you emphasize that it supports stable modeling rather than rewriting reality.
Interpretability costs grow when you use more complex transformation families, and you should weigh those costs against the benefits, especially in settings where explanations and governance are important. A log transform is widely understood and easy to communicate as percent change reasoning, while a fitted power transform parameter can be harder to explain without sounding like you are hiding the ball. Complex transforms can also make it harder to compare results across projects because each model may use a different parameter choice based on its data, reducing standardization. The exam often expects you to choose the simplest effective transform because simplicity supports communication and reduces maintenance burden. This does not mean avoiding Box-Cox. It means using it when it solves a problem that simpler transforms could not solve reliably. When you discuss interpretability costs explicitly, you show that you can balance statistical benefits with operational clarity.
Documentation of chosen parameters is critical because training and inference must remain consistent, and a fitted transform without recorded parameters is a reproducibility failure. If you fit a Box-Cox lambda on training data, that exact lambda must be applied to new data, or the model will receive inputs on a different scale than it was trained on. Documentation should include the transform family used, any shifts applied to handle zeros or negatives, the fitted parameter values, and the rationale for choosing that configuration. The exam treats this as governance because undocumented transforms create hidden dependencies that can break deployments and undermine auditability. Documentation also supports lifecycle management because if drift changes the distribution shape, you can revisit whether the transform still fits and whether refitting is justified. When you document transforms carefully, you turn a potentially fragile pre-processing step into a controlled, versioned part of the modeling pipeline. Transformations also link directly to assumptions for regression and statistical tests, which is one reason they appear frequently on exams. Many tests and regression interpretations assume something about residual behavior, such as approximate normality or constant variance, and skewed, heavy-tailed variables can violate those assumptions. A transform that stabilizes variance and reduces skew can make these assumptions more plausible, improving the reliability of intervals and hypothesis tests. This is not about forcing the data to look normal for cosmetic reasons. It is about aligning the modeling framework with the data's behavior so that the inferences you draw are not systematically biased or overconfident. The exam expects you to recognize that when assumptions are violated, you can respond either by choosing robust methods or by transforming the data to better satisfy assumptions, and Box-Cox is one option in that toolkit. When you connect transforms to assumptions, you demonstrate that you understand the purpose of the transform in the statistical workflow. A useful anchor memory is Box-Cox adjusts shape and spread with one knob. Shape refers to skewness and tail behavior, spread refers to variance behavior across the range, and the knob is lambda, which you tune to match what the data needs. This anchor helps because it reminds you that Box-Cox is a family, not a single transform, and that its value is in controlled flexibility. It also reminds you that you should not treat lambda as a truth about the world. It is a parameter that helps the model see the world in a more learnable way. The exam rewards this understanding because it leads you to choose Box-Cox when log is insufficient and to validate and document the parameter choice rather than applying it casually. When you use the anchor, you keep your reasoning centered on why you are transforming, to adjust shape and spread so the model assumptions are less violated. To conclude episode 63, the key decision is recognizing when log fails and then choosing a broader transform that better matches the observed distribution and residual cues. If you apply a log transform and residuals still show non-uniform spread, or the distribution remains noticeably skewed, that is a signal that the log shape is not the best fit for this variable's behavior. In that case, a fitted power transform family like Box-Cox is a sensible next step for positive value data because it allows you to tune the degree of compression and variance stabilization rather than accepting the fixed log shape. You would fit the transform parameter on training data only, apply it consistently to validation and inference, and confirm improvement using held-out error and more stable residual behavior. You would then communicate that this transform is a model inconvenience and translate any key effects back into business language, emphasizing ranges and proportional impacts rather than raw transformed units. This is the exam-ready posture. Log is a good first move, but when it does not solve the shape and variance problem, you reach for a flexible family, validate it honestly, and document it so the transformed story remains consistent and explainable. Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.